Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're going to begin to look at electrophilic aromatic substitution. That is, we're going to answer the question, how does benzene undergo reaction compared to other alkene molecules? Now, it turns out there is high electron density above and below the plane of the aromatic ring. And just like the pi cloud in an alkene, this pi cloud will attract positive species, i.e. electrophiles or Lewis acids. Now, in the case of benzene, however, rather than undergoing electrophilic addition, we're going to discover that the typical reaction of aromatics are electrophilic substitution reactions because addition would destroy the aromaticity of the ring. So if we were to draw a benzene ring, because we get electrophilic substitution, and let's just put dots for a carbon so you can tell that this is a benzene. There would be some leaving group, which is typically the H plus. Okay, typically hydrogen would be pulled off as H plus. We add an electrophile, some E positive molecule. And we have our leaving group leave. And we get E attached to the ring. And we get the leaving group, L plus. Now, electrophilic aromatic substitution is one of the most important reactions in organic synthesis. The general mechanism requires formation of a powerful electrophile. The electrophile adds to the aromatic ring, producing an intermediate species in which the aromatic ring has been disrupted. We produce what is called a resonance Benzenonium ion. So let's look at the first step of electrophilic aromatic substitution, step 1. The attack of the electrophile. The electrophile attacks the pi bond and attaches to the ring. So benzene has H's here, and our electrophile attacks. This is usually the slow step of the reaction because you are producing a carbocation. But once the attack has taken place, you will notice that aromaticity has been disrupted. And we get a high energy intermediate. But the intermediate is resonance stabilized. That is, I can move these two pi electrons to that bond. Okay. Double bonds would now be here, and the plus would be located here. And if I produce one more resonance structure, these pi electrons could move here, and that would put the plus up here. Now, all resonance structures are simply representations that localize bonds, and none of them exist. What exists is the resonance hybrid. This resonance structure is referred to as a resonance stabilized Benzenonium ion. It is a high-energy carbocation that forms. The resonance hybrid would look something like this. We have an H, we have an E. And I'll use black. We get a delta plus here, a delta plus here, and a delta plus here. The positive charge is delocalized over those positions. The positive charge is distributed over 3 of the 5 available positions, 2 ortho and 1 para. The 2 metal positions carry no formal charge. They're slightly positive due to the closeness to positive charges, but that's by electronegativity. This step is very similar to what we saw in alkenes. What do I mean? If we compare this, say, to a simple alkene, electrophilic attack was the first step in alkene reactions. So if you hit this with an electrophile, you produced a carbocation. Formation of the carbocation is the slow step. In most of the reactions we're going to look at, we're going to discover that this is actually the slow step, which makes sense. It takes energy to disrupt the aromatic ring, and it's not easy to do. Step 2 is the substitution reaction. So we'll rub this out. Step 2 is elimination of a proton attacked by base. And a resonance stabilized benzenonium ion has some base come in. Let's make it negatively charged. It may or may not be. It grabs the proton, and these 2 electrons restore aromaticity. And so we get our substituted benzene plus the base combined with H. Now sometimes this new base molecule will fall apart, and we'll see examples of that. What's interesting is this is not the same as what occurs in alkene chemistry. In alkene chemistry, the carbocation does not eliminate a proton. If we had addition, Markovnikov addition, we then get nucleophilic attack. If the electrophile added to carbon with most hydrogens in the second step, the electrophile would add next. So alkenes go by electrophilic addition, and we'd get some nucleophile attached to our CH2. So alkenes undergo electrophilic addition. Why did we not add a nucleophile here? Why did we not do electrophilic addition like an alkene and leave H here, E, and then add a nucleophile? The reason is this is too high energy. This pathway is far higher energy than we would expect to be followed because we have permanently disrupted the aromatic ring. This is too high energy and it's not followed. The energy of activation for substitution is lower than addition. Substitution gives you the more stable, resonance stabilized aromatic product. However, looking at this mechanism, we have to admit that in the first step, the slow step, we are disrupting the aromatic ring. Because of this, we require very strong electrophiles. These electrophiles usually have to be prepared and used on the spot. They're usually obtained by using strongly acidic Lewis acids as catalysts. These will react with one of the reactants and yield the electrophile, which then can attack. So let's begin by looking at some examples of electrophilic aromatic substitution. Each one I'll give you the reaction first, and then I'll show the mechanism. So let's begin with the first one, which is halogenation. Halogenation with electrophiles works well with chlorine and bromine. In the halogenation reaction, we take a benzene and we react it with the halogen. This sounds similar to, for example, we may use Br2. This sounds similar to what you might expect for an alkene. But Br2 by itself does not react with benzene. We need a catalyst. The catalyst we use can be iron, but usually it's FeBr3. The reason we can get away with iron is Br2 plus iron will produce FeBr3. Br2 and FeBr3 will allow us to make bromobenzene. Notice we did not get addition of Br2 across the double bond, but rather we get what is called electrophilic substitution. How does this reaction occur? Well, as I said, you can use iron. If you use 2 irons, and those 2 irons react with 3 bromines, you will produce 2 FeBr3. FeBr3 will then react with the bromine molecule, Br2, and produce our electrophile. FeBr4 minus is produced, and the electrophile Br plus. Now, Br+, bromine is quite electronegative and does not prefer the positive charge. Hence, it is a very powerful electrophile. In fact, Br+ stays closely associated with the FeBr4-. But in the presence of a benzene ring, Br+ can act as an electrophile that attacks the benzene. If Br+ does attack, we will produce a resonance-stabilized benzenonium ion. Now, you'll notice last time we drew, we had an E here. Well, this time it's a bromine. And I get a positive charge here. Now this is resonance stabilized. I will draw the resonance structure this time, but I'm not going to draw it every time because the structures are exactly the same. You're just changing the substituent. You'll notice that I am drawing the exact same resonance structures I drew last time. So these two electrons moved here. This is my resonance stabilized benzenonium ion. Now at this point, what is interesting is that the resonance stabilized benzenonium ion gets attacked by the FeBr4-. The FeBr4- attacks the H. The H dumps in some electrons and restores the double bond. Once that happens, the H has been pulled off. I get bromobenzene. And FeBr4 falls apart, making HBr and producing FeBr3. Because FeBr3 is reformed in the reaction, FeBr3 is the catalyst. Now notice this reaction, we could replace a different Lewis acid with FeBr3. We could use aluminum AlBr3. If we used AlBr3 with Br2 produces AlBr4-. And AlBr4- would attack the proton, giving us HBr and restoring AlBr3. Both AlBr3 and FeBr3 are Lewis acids. Notice I could change to chlorine and make chlorobenzene this way. I could use Cl2 and FeCl3. Or I could use Cl2 and AlCl3. All work. Note the slow step is formation of the resonance-stabilized benzenonium ion. Even though the benzenonium ion is resonance-stabilized, it's still unstable. It's a typical carbocation, and you have disrupted aromaticity. So the second step is fast, reforming the aromatic ring. Let's look at the next reaction, nitration. Nitration is a process or reaction that puts a nitro group on a benzene ring. In this case, we react benzene with a mixture of nitric and sulfuric acid. HNO3 and H2SO4. This reaction will put an NO2 group on the ring. How? How does this happen? Well, the first step is formation of the electrophile. It turns out that HNO3 is actually HONO2. If I react it with H2SO4, H2SO4 is a stronger acid. Hence, H2SO4 will protonate the nitric acid. Now I'll get HSO4 minus plus now, if I do this, the H2O is a good leaving group, and I produce the electrophile NO2+. Now, NO2+ is called nitronium ion. Nitronium. Ion. NO2+ nitronium ion, if I draw its Lewis structure, looks like this, where the nitrogen has a formal charge of +1. Because of the positive charge on the electronegative atom, nitronium ion is a powerful electrophile. When reacted with benzene, NO2+ will add via a carbon-nitrogen bond, and you will produce your resonance stabilized benzenonium ion. Oh look, it's the exact same thing as the last structure, except instead of the Br, I now have the NO2. You could draw all three resonance structures. I am not going to take the time to draw the resonance structures every time, but you should be able to. You should be able to move the pi bond here and then create the next set of resonance structures. What's interesting now is what happens next. The benzenonium ion is attacked by our base, HSO4 minus. Sulfuric acid has lost the proton, and this HSO4 minus grabs the proton. Those two electrons come back in and restore our pi bond. And so we end up getting our nitrobenzene plus H2SO4. H2SO4 reforms and hence is our catalyst. So H2SO4 acts as a catalyst. Powerful electrophile NO2+ attacks, producing a resonance stabilized benzenonium ion. Okay. What other powerful electrophiles are there? Well, we can produce electrophiles called carbocations. If a carbocation attacks the ring, we will produce an alkylbenzene. Hence, this is called Friedel Crafts alkylation. Now, producing a carbocation to act as an electrophile is tricky. But we have been exposed to carbocations in 3 sections of this course. We have seen carbocations when reacting with alkyl halides. We would see them in SN1 and SN2 reactions. We know they're relatively unstable. Well, it turns out that if you hit an alkyl halide with AlX3, you can produce your carbocation, call it R+, plus AlX4-. Well, X is some halogen, chlorine, bromine, and R is some alkyl group, methyl, ethyl, etc. We also learned that alcohols, secondary and tertiary alcohols, in the presence of acids such as H2SO4 or phosphoric acid, H3PO4, can undergo protonation, protonate the lone pair, make the good leaving group water, and you can get carbocation plus water. And lastly, we've seen carbocations when we've taken alkene and carried out Markovnikov addition. So if we take some alkene and do Markovnikov addition of H+, so we react it with something like HCl, we'll get Markovnikov addition, a carbocation, and then the nucleophile would attack. But if we add some Lewis acid to this, like AlCl3 for example, we can grab that chlorine, make carbocation, and get AlCl4-. We can slow down nucleophilic attack. If we do this in the presence of benzene, the electrophile carbocation can attack the aromatic ring. So we have seen in our studies 3 generations of carbocations. We can make carbocations from alkyl halides, we can make them from alcohols, and we can make them from alkenes. Let's begin with an example that exemplifies how to make it. How we do a reaction with an alkyl halide. Suppose I take benzene and I react the benzene, I don't know, with tert-butyl chloride. Tert-butyl chloride. And we use AlCl3. Well, this reaction will take place and you will actually put on the aromatic ring a tert-butyl group. And you'll make tert-butyl benzene. How does that happen? Well, the tert-butyl chloride reacts with the AlCl3. The Lewis acid, AlCl3 reacts with tert-butyl chloride and removes the chlorine, yielding tert-butyl carbocation. plus AlCl4 minus. The tert-butyl carbocation reacts with benzene. To produce the same resonance stabilized Benzenonium ion. The only difference is where there were the other substituents, bromine and nitro, we now have a tert-butyl group. Again, I'm not going to draw all the other resonance structures. You should be able to generate them. AlCl4 minus attacks the proton. 2 electrons dump in, restoring the pi bond, and we get the tert-butyl benzene. Tert-butyl benzene, we get, of course, HCl and AlCl3. So the AlCl4 minus falls apart, restoring AlCl3, which becomes a catalyst for the reaction. So this looks exactly the same as what we've seen in bromination and nitration. Nothing new. One interesting point of difference is that we have to watch for 1,2 shifting, rearrangement. Carbocations do undergo 1,2 shifts, and so we have to be careful so that we produce the more stable carbocation. For example, if we attempt to carry out reactions with, for example, propyl chloride and AlCl3. So, there's propyl chloride, AlCl3. You will get a mixture of isopropyl benzene and propyl. And that mixture is major isopropyl, 70% isopropyl and only 30% of the propyl. Why is that the case? Why do we get isopropyl benzene? Well, we would produce AlCl3 would grab the chloride and you'd get propyl carbocation. Primary carbocations are extremely unstable. And so you'll get a 1,2 hydrogen shift. A 1,2 hydrogen shift will produce isopropyl carbocation, which is more stable because the primary carbocation converts to the secondary isopropyl carbocation. Now, in actual fact, you know, it's rather amazing that the carbocation itself, that we actually see any of the primary carbocation. Usually the 1,2 shift happens. To form the propyl, you must get intermolecular collision. This suggests that once the electrophile forms, it's so reactive, it comes in really fast on the aromatic ring. Okay, let's look at another example where the shift is so strong that you don't get any of the unshifted product. The reason we see some unshifted product is the shift goes from primary to secondary. And secondary is more stable. But if you shift from primary to tertiary, tertiary is so much more stable than primary. That shift happens so fast, you don't see any of the primary product. So this time we're going to take benzene. We're going to react it with CH3 twice CH2Cl, isobutyl chloride, and AlCl3. In this case, if you use isobutyl chloride, you get 100% tert-butylbenzene. You get no isobutylbenzene. Well, AlCl3 does grab the chloride, and you do get the carbocation, the isobutyl carbocation. But what kind of carbocation is this? This is a primary carbocation. If you do a 1,2 hydrogen shift, you'll get CH3, I'll draw it the same way, twice CH3. Oops, get rid of the H. CH3. The H shifts over. Well, this is a tertiary carbocation. This shift to the tert-butyl group causes only tert-butylbenzene to form. So you have to be careful. Watch for rearrangement. Watch for shifted products. You cannot produce good yields of propylbenzene or good yields of isopropylbenzene with the Friedel-Crafts alkylation. Okay. Now, let's look at how these other carbocations would form. They likewise you have to be careful and watch for rearrangement. But if I take, say, isopropyl alcohol in H2SO4, the acid of H2SO4 will protonate the alcohol. Sulfuric acid is a very strong acid. You'll make the good leaving group water. and you'll get minus H2O carbocation. Again, you have to check for rearrangement. In this case, I've made the most stable carbocation. And the secondary carbocation can attack. Likewise, the carbocation can be prepared from the alkene, for example, propene. If I react propene with HCl and AlCl3, the AlCl3 will scavenge the chloride, the H will add Markovnikov, and I will produce the same carbocation, isopropyl carbocation. Again, I got to watch for shifting, but I'll get AlCl4 minus. Both these carbocations can attack the aromatic ring. Again, watch for shifting. Okay, so Friedel-Crafts alkylation will put an alkyl group on the aromatic ring. We can make it 3 different ways, from alkyl halides, alcohols, or alkenes. We have to watch for that. But rearrangement will occur, and it's not useful for making molecules like propylbenzene from propyl chloride or isobutylbenzene. How could you make a butylbenzene or a butylbenzene or a propylbenzene? Well, we have to take a different approach. We have to carry out what is called Friedel Crafts Acylation. In Friedel's Crafts Acylation, we use an acyl chloride, some carbon chain that has a C double bond O Cl. We react that with AlCl3. The AlCl3 will grab the chlorine, and I will produce an acylium ion. Let's put the double bond O down, running out of room. But the acylium ion, unlike normal carbocations, is not susceptible to a shift because it is resonance stabilized. So this is a resonance stabilized acylium ion. The resonance stabilization helps prevent shifting. So R could be a CH3CH2, in which I would get the following acylium ion. For example, I could use CH3, CH2, C double bond O Cl in the presence of AlCl3. And I would produce the CH3, CH2, C double bond O plus. Of course, the side product to that is AlCl4 minus. So you get AlCl4 minus up there. Now, if I react this with benzene, let's make that a little larger. If I react that with benzene, the resultant Acylum ion will add onto the aromatic ring. And my product will be a ketone. So I can draw the ketone. So let's draw that ketone. Now, of course, as usual, I get the resonance stabilized Benzenonium ion. So here's the resonance stabilized Benzenonium ion. And I'm not going to draw the resonance structures. The AlCl4 minus will come in. It will grab that proton. These two electrons will reform the pi bond. So let's put an arc here. And so pull the proton off. And I have ethyl phenylketone. So Friedel acylation is an excellent way to make ketones on aromatic rings. But it also can give you the unshifted alkylbenzene. How? If you take zinc mercury, mercury is a liquid metal. It can act as a solvent to metals. Many metals will dissolve in mercury. Zinc is a fairly strong reducing agent. If you want to reduce its activity, lower the reaction rate, you can dissolve it in mercury and slow down the rate of reaction. Zinc-mercury compounds are called zinc amalgams. Zinc amalgam reacted with HCl and heat and I may or may not show the heat. Zinc, mercury, HCl, and heat will get rid of the double bond O and replace the double bond O with two hydrogens. And we'll get high yields of the molecule we could not make because of 1,2 shifting in Friedel-Crafts alkylation. And so we'll get good quantities of propylbenzene. Friedel-Crafts acylation is a real nice methodology for making straight chain alkylbenzenes if you carry out the reduction on the ketone that is formed. Very good reaction for putting a linear side chain on a benzene ring. The last reaction I want to look at is sulfonation. Sulfonation. Sulfonation of aromatic rings, reaction with H2SO4. Now, H2SO4 in its pure form, concentrated H2SO4, is called fuming sulfuric acid because it gives off SO3 gas. You see, H2SO4 has this structure. And just like water, which can react with itself to produce hydroxide and H3O+, H2SO4 can react with itself. If it's in pure form, H2SO4 can protonate itself. You get HSO4 minus, but you will also get HOH plus S double bond O double bond O OH. Now water is a good leaving group. We can lose water. If you lose water, you'll get S double bond O double bond O OH. And if you do the electron counting, you'll find out sulfur is positive. This can quickly lose H+. That is, HSO4 minus could come in and grab the H+. If it does, you'll get H2SO4, so minus H+. That just goes on the HSO4 minus, remaking the H2SO4, and you end up with sulfur trioxide, SO3 gas. Sulfur trioxide, SO3 gas, has 3 electronegative oxygens. Sulfur can have more than 8 electrons because it's in the third row and has accessible d orbitals. But I can draw resonance contributors where I move the pi electrons out on oxygen, and I get structures like this. Formal charge negative on oxygen, positive on sulfur. Whether you utilize these other resonance contributors, and I can draw 2 more with single bonds to the other oxygens, so I can keep drawing these. All of these resonance contributors aid in the establishing that sulfur is quite electrophilic. Sulfur is available to attack pi electrons, and because of this, fuming sulfuric acid, SO3 gas, is an excellent electrophile which can attack benzene. All right, so let's take a look at this. We have a benzene, and we react it with S double bond O, double bond O, double bond O. Sulfur gets attacked by the pi cloud of electrons, which pushes out pi electrons towards the oxygen, And when we get that, we get our resonance stabilized Benzenonium ion. Exactly the same as the others, except this time we have an SO minus double bond O, double bond O. We get a plus here. Now there is H2SO4 minus floating around, but let's grab the proton. What's interesting is the O minus on sulfur can actually contribute to grabbing the proton. And if it grabs the H, we can restore aromaticity, and we get this molecule. And if I draw that molecule just a slightly different way, we've seen this molecule before. When we took alcohol chemistry, we just never learned how it formed. This is the molecule benzene. Sulfonic. Acid. Benzene sulfonic acid. Now, benzene sulfonic acid formation is a bit of an exception. If you recall, I told you that addition of the electrophile is a slow step, and indeed, in this case, it is the slow step. But the abstraction of hydrogen is, in this case, not as fast as usual. And so if we replace H with a deuterium, the reaction, this fast step, will slow down. Okay? Pulling off H has nothing to do with the first step. But pulling this H off has everything to do with the second step. What happens is, when we go to deuterium, this faster step slows down enough to now become the slow step. This is a very rare occurrence where we see a fast step being only slightly faster than a slow step. And when you change it to deuterium, our fast step becomes the new slow step. When that happens, we will see a kinetic isotope effect. A kinetic isotope effect is a slowdown caused by changing isotopes. If we change hydrogen with deuterium, we see a slowdown. But we shouldn't see a slowdown if the second step was faster. So when it's hydrogen, you get this. But if I redraw the reaction, and the first step is exactly the same, this time I'm going to just write SO3. But we have deuteriums on our benzene. Okay, so we have deuterobenzene. If we're using deuterobenzene, I'll see this guy form. You'll grab the deuterium, you'll form benzene, and I'll just draw the product. This time we get OD, not OH. It turns out that the first step is only slightly faster, and a slow step is the deuterium abstraction. Because of this is a kinetic isotope effect. Now normally kinetic isotope effects around in the alkene, one case, cause a slowdown rate of about factor of 7. In this case it causes a slowdown rate about factor of 2, and this kind of decrease may be attributable only to this shifting, the fast step all of a sudden becoming slower. So we do see a kinetic isotope effect for sulfonation. Well, there you have it. If I summarize this reaction, benzene can react with H2SO4 that is fuming, pure H2SO4, so H2SO4 SO3, to make benzenesulfonic acid. And there's benzenesulfonic acid. Why don't we summarize this? Draw benzene in the middle. And summarize all the reactions we've learned today. We've learned that you can take Br2 with FeBr3 and produce bromobenzene. We can take Cl2 with AlCl3 and we can produce chlorobenzene. We can take alkyl halides, RCl, or alcohols and acid, or alkenes with HCl, and AlCl3. And we'll put alkyl on the ring. But watch for rearrangement. We can take RC double bond O Cl and AlCl3. And we will make our ketone. React that with zinc mercury, HCl, and heat. We can get rid of the oxygen and get H2R. We learned that if we hit this with HNO3, H2SO4, we can put a nitro group on benzene. And lastly, if we use H2SO4 and SO3, we can get benzene sulfonic acid, SO3 H. All electrophilic addition, all electrophilic attacks, all undergoing electrophilic aromatic substitution, all reactions producing very powerful electrophiles. Well, I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.